Dear students, welcome back. We have reached section 5.4.2, and here we will generalize our one-dimensional asset price process towards multiple dimensions. So we will look at multiple stocks simultaneously, and we end up with a multidimensional market model. Let's first define the basic settings. We are dealing with randomness, which is determined by a d-dimensional Brownian motion. So vector Wt consists of W1t, W2t, up to Wdt, a d-dimensional Brownian motion, and we are considering M stocks. And they have the underlying price processes as follows. dSyt is equal to alpha it sit dt, plus, and we do this a little differently here, plus Si times the sum, I runs from 1 to D, sigma ijt dwjt. So this is the underlying price process for each I. I runs from 1 to M. So these are M equations, where D Brownian motions play a role in this sum. So in order to make this a little better manageable, we will look a bit carefully at these Brownian motions. And typically stocks are correlated. When one stock goes up, other stocks may go up as well. Think of all the stocks in the medical sector that may go up altogether. Or when one particular company has a very good product, the stock price may go up, and then maybe other stock prices may go down, a negative correlation, but typically stocks are correlated. And this correlation mechanism should be incorporated in the stock price process. And in order to do that, we define sigma it, well, that is the square root of the sum j runs from 1 to d of sigma square ijt. And that is typically greater than 0 because the uncertainties, the volatilities, sigma ij, they are typically larger than 0. So a sum of squares and the square root of it, that is a positive number. And we will look at a modified process, process bit, and that is the integral from 0 to t of the sum, j runs from 1 to d, of sigma ij u divided by sigma I u, the sigma I that we have just defined, u, times dwju. So this sum, a normalized sum, the sum that we also encounter here, this sum, that we give a different name, and that is bit. And we will look in more detail into this bit. So let's first note that bi0 is equal to 0. And again, I runs from 1 to M. So what else do we have? Well, we want to see if we can make the statement that the bi are Brownian motions. So we will work towards the Levy characterization of Brownian motion. And for that, we need 4 statements, if you remember. bi0 is equal to 0. bit has continuous paths. Well, that is also the case in this setting. It is a martingale. Well, you see it's an integral of a sum of Brownian increments. So then it's well known that we're dealing with an Ito integral in this case. And if we look at the quadratic variation, and we look at it in differential form, we look at dbit. Now, then we look at the differential form and we square this. So here should be a square. And this is the sum, j runs from 1 to d, sigma ij square t, divided by sigma I square t, which is the sum of these terms, dt, because dwju is dt, as you know. And because this sum here is in fact sigma I square t, then this is equal to 1. And then we see that indeed the quadratic variation in differential form gives us dt, so the quadratic variation is equal to t. Now, with all these statements, we know that by Levy's characterization, BIT, t greater or equal to 0, is a Brownian motion under P. And we can use it to redefine our stock price processes. So for each I is 1 to M, we can write D as IT is equal to alpha IT as IT dt, that hasn't changed, plus a reformulation. So again, if you look at this definition, and you compare it with this part, then that sigma I should go to the left-hand side, and we end up with sigma IT SIT dBIT. So that's sigma IT that comes from that equality that we have just seen. Now we want to work, and we would like to consider this in a bit more detail. We want to work with it, and there is an important notion, is that the BITs, they are not independent. So B1T, B2T, up to BDT, little t between 0 and capital T, that is not a d-dimensional Brownian motion, because these BIs are not independent. And we can see that when we look at the cross variation. And the fact that it's not a Brownian motion means that we cannot use, for example, the d-dimensional Girzanov theorem, because that is all based on independent Brownian motions. So we look at the cross variation for I not equal to K. We look at dBIT, dBKT. And if we write that out, then dBIT is the sum J runs from 1 to D, sigma IJT divided by sigma IT dWJT. And then if we look at dBKT, then we replace I by K. So that is again the sum J runs from 1 to D, sigma KJT divided by sigma KT times dWJT. And of course, we can also write this out. So it's 2 times the sum, the same sum, J runs from 1 to D. So we have the sum J running from 1 to D. And then we have here in sigma IJT divided by sigma IT times sigma KJT divided by sigma KT times dt. And this term here, that sum of sigma IJT sigma KJT divided by sigma IT sigma KT, that we call rho IK. So it's not equal to 0. You see, this is not equal to 0. So in other words, that cross variation, the cross variation BI/BK, that is in fact the integral from 0 to t of this rho IK term, rho IKU du. And now let's apply Ito's product rule to look at it a bit closer. So Ito's product rule, the D, the change in BIT, BKT. Let's look at this. It is, of course, by definition, BIT, the change of BKT, plus BKT, the change of BIT, times the change in BIT times the change in BKT. And this one we have just computed. That was from the previous page. That is the one that we just computed. That was rho IK dt. So that one we have just computed. The other ones we just copy. BIT dBKT plus BKT dBIT. And for that one we substitute plus rho IK dt. And if we look at that in integral form, we see that BIT, BKT, well, it is equal to first of all, the term with 0 for T0, but that is equal to 0. So that is not written down here, plus the integral from 0 to T, BIU, dBKU, plus the integral from 0 to T, BKU, dBIU, plus the integral from 0 to T, rho IKU du. So what we see here is that it's not equal to 0. it is in fact a specific number. And we can see that in more detail if we look at the covariance. So these off-diagonal elements, if you wish, they are not equal to 0. So if we look at the covariance between BI and BK, that is by definition the expected value of BIT times BKT minus the expected value of BIT times the expected value of BKT, and these are 0. So that one cancels out. And then we end up with this expected value of BIT BKT. So we put an expectation in front. We recognize here two Ito integrals. So the thing that remains is the expected value of the integral from 0 to t, rho IKU du. So if we finalize this by saying an expected value the BIT times BKT, that is the expectation of the integral from 0 to t rho IKU du, and that is the covariance BIT BKT. So that is a notion that these are not independent Brownian motions. BI and BK, they are not independent. We come back to our original price process. We will look at the discounted price process, DTSIT, where little t runs from 0 to capital T. And we have that discount term, the discount term dt, that is e to the power minus the integral from 0 to t, ru du. And you may remember that the change in discount term is then equal to minus rt dt little dt. So that we will also be using. And of course, remember, this is our price process with the b's here. And later we will change this back to a formulation with w's here. DSIT is equal to alpha IT SIT dt plus sigma IT SIT dBIT. And I runs from 1 to m. These are m processes, and these Brownian motion and these processes here, they are correlated. Now the aim is to find an equivalent measure, P tilde, such that all the discounted price processes are martingales under P tilde. And the reason for this being that we again want to have a fair price process. So the expected value for the process in the future, the best thing we get for that is the value now. That is a fair price process, and that is what we would like to achieve. And again, we will do in multiple dimensions the steps that we did in one dimension. So if we look at this discounted price process, the change in discount term dt times SIT, we look at that with the help of Ito's product rule. So it is dt dSIT plus SIT times the change in the discount plus the change in the discount times the change in the stock price process. Well, the change in the discount, if you remember, that goes with dt. So everything that comes from here, the dt term or the dw term or the db term, they will give us terms of higher order, dt squared, which is equal to 0, and multiplied these two gives us the cross variation, which is equal to 0. So this term will cancel out, yeah. And we can substitute for dSIT. We can substitute the term over here. And for dd, well, we just wrote it down, and we know it's minus r times d times dt. So let's do that. We say this is the discount process, and then we open the bracket and we write down the dynamics for SI, and we close the bracket again. And then we have the second term, that is SI times minus dt rt dt. So that is the second term. This term was canceling out, as we mentioned. So we can collect the dt terms, and that gives us alpha it minus rt. And then we have these brackets again. And then out of brackets, we have the discount term times the SI term, the discount term times the SI term times dt. And the part that remains here is Si sigma I dBi of t. And now comes this notion that I just mentioned already. We cannot use Kirsanov's theorem now because these bi's are not independent. So what is the solution? We go back to our W terms. So let's rewrite them in terms of the original Brownian motions. And doing that, we look at the change of the discounted stock price process, the discounted ith stock price process. And that is this part that we have just seen, alpha it minus RT times the discount term at t times SI at t dt, plus the discount term at time t times SI at time t. And here we write back these the dBIs, we write them back as the sum. J is 1 to D, sigma IJT, dWJT. So we are having this now. We can take the ds out of brackets. So here is the discounted stock price process. And what remains in these square brackets is alpha it minus RT dt plus this sum j runs from 1 to d sigma IJT dWJT. And remember what we did now in order to get to a risk neutral measure. So what we would like to find is a vector valued theta process, an adapted process consisting of theta 1t up to theta dt, such that alpha it minus RT is equal to the sum j runs from 1 to d, sigma IJT theta jt, and that is for I1 up to m. And these equations here, these M equations, we call the market price equations. So we would like to find this relation, because if we find this relation, then we are in a good situation. Then we can connect, we can rewrite this with this sum, and then we can connect this term with this term. Then, in fact, we would have that the dynamics for the discounted price process would be DISI times the sum j runs from 1 to d sigma IJT. And then we have this special process that we are used to from the one-dimensional case, theta jt dt plus dWJT. And here you may recall this looks like dW tilde jt. And if we can write this as a dW tilde jt, we will end up with a martingale. So if we let now, first of all, if we let W tilde jt be this integral from 0 to t, theta ju du plus wjt, like we just mentioned, and we need to do, we do Kirsanov's theorem, so we need to have our z process, zt, e to the power minus the integral from 0 to t, the sum j runs from 1 to d, theta ju dwju, minus 1/2 the integral from 0 to t, the sum j runs from 1 to d, theta j squared u du. If we define this, then as you see, this looks very much like the one-dimensional case, only now we are dealing with a multi-dimensional setting. For the rest, this is the same. Well, this measure change we do based on zt, right? Z capital T. And we just get that by replacing the small t here by the capital T. And we also call that z. So that's the next step. The third step, z is equal to zt, is then just substituting for little t here, capital T here, and then we end up with this expression. And then we have our measure change, p tilde a, that is then the integral over a of zdp for all a in the filtration F. Now, with this, we can apply Kirsanov, right? With this, we can apply Kirsanov, and that is as follows. We have the multidimensional Kirsanov theorem, that tells us there is a vector valued process, W tilde IT, 1t, W tilde 2t, up to W tilde dt, little t running from 0 to capital T. It is a d-dimensional Brownian motion under P tilde, right? And moreover, with this, we can write these dynamics that change in the discounted SI process. We can write it as dt SIT times the sum, J runs from 1 to D, sigma IJT, times these Brownian increments here. So these Brownian increments, d W tilde JT. And that is, of course, a favorable formulation, because now we see that this is a martingale under the P tilde measure. And that is what we want, right? So if we look at it in integral form, it says the discounted price process, the discounted ith price process, dt SIT, it's equal to SI0, because D0 is equal to 1, plus the integral from 0 to t, du SIU, the sum J runs from 1 to D, sigma IJT, dW tilde JT. And this is a sum of Ito integrals, and therefore this discounted ith stock price process is a martingale under P tilde. And that is what we wanted to achieve. And you recognize that this is a clean generalization of the one-dimensional case. Nothing strange going on. This is a straightforward generalization of the one-dimensional case. Well, what's next? Well, the existence of P tilde depends on whether these market price equations have a solution. Yeah, whether we can find a theta 1t, a theta 2t, up to a theta dt. So the existence of P tilde depends on whether the market price equation have a solution, whether we find a theta 1t, theta 2t, up to a theta dt. And we call P tilde as before the risk neutral measure, because under this changed measure, the discounted stock price process is a martingale. So we have a fair discounted price process. And formally, this risk neutral measure is defined as follows. A probability measure P tilde is called risk neutral if certain properties are satisfied. First of all, when we have equivalent measures, P tilde and P are equivalent measures, which means P tilde 0 is equal to P 0. And if the discounted price process DTST, little t between 0 and t, is a martingale under P. Now, in fact, we can do exactly the same generalization and the same exercise for the discounted portfolio process, DTXT. We can also see that under the risk neutral measure, we can connect that to the discounted option price. And by that, we also have a generalization of the one-dimensional case in case of this process DTXT in multiple dimensions. Well, it is on the slides, so I will not talk too much about that here. I'd rather go to, it is pretty straightforward. And we end up, of course, with, again, we write out the dynamics dxt, and we look at, by means of Ito products rule, we look at the discounted portfolio process, and we write it out in detail. We end up with the formulation that the discounted portfolio process is equal to x0. The sum I is 1 to m, the sum j is 1 to d, the integral from 0 to t of delta IU, delta stocks, the discount factor du, SIU, sigma IJU, dW tilde JU. And we will find that comes in handy a little bit later on. I'd rather go with you now to the concept of arbitrage, because that is a very important concept. Basically, arbitrage means there is a possibility, an opportunity to make a profit, which is larger than just putting money on a bank account without any risk. And that, if you think about it, that cannot be. If there is an arbitrage opportunity in the market, if there is a possibility to make money larger than just putting money on a bank account without taking any risk, then everybody would do that. And by that, either a counterparty would come into extreme troubles, or the arbitrage opportunity would disappear. So let's first look at the concept of arbitrage, look at the definition, and see what implications this has in our setting with a writer and a trader, a holder of an option. So what is an arbitrage opportunity? An arbitrage is a portfolio process X, T, 0 less or equal to little t less or equal to capital T, which satisfies the following. Well, at initial time, say X at initial time, X0 is equal to 0. And then the probability that X at final time is larger or equal to 0 is equal to 1. And moreover, the probability that X at final time capital T is larger than 0 is greater than 0. So we start with nothing, and the probability that we have at nothing or more is 1, and the probability that we have more than nothing is greater than 0. And that is an arbitrage opportunity. Yeah? So we have nothing, and in the end, we have more than nothing. So starting with nothing, you're guaranteed no loss at T, that is this one. And moreover, you have a positive probability of winning out of nothing. That is this statement. Well, there is a reformulation possible. So the definition of arbitrage is equivalent to this other definition. So if we call this definition star, then this is equivalent to saying for any initial value A, there is a portfolio process which we now call capital YT. And again, little t is between 0 and capital T, such that, first of all, at the start, y0 is A, so there is an initial value. At the start, y0 is A. Then, secondly, the probability of the discounted process, the discounted y process at final time capital T, the fact that this is greater or equal to the initial value, that is equal to 1. And thirdly, the probability that that discounted y process at final time is greater than the initial value is greater than 0. So this was 1 and this was 2. Now, it's relatively easy to argue from 2 to 1, right? From 2 to 1, we just make little a equal to 0, and then we end up essentially with this process here. 1 to 2 and from 2 to 1. That is relatively straightforward. And it is, for example, proved by setting y0 equal to A, and then yt that should then be set equal to y0 plus xt divided by the discount term, dt. And with that, we can prove this, the equality between these two formulations. And with that arbitrage opportunity, we reach theorem 5.4.7, which is the first fundamental theorem of asset pricing. And that first fundamental theorem says the following: if a market model has a risk-neutral measure, P tilde, then it does not admit arbitrage. So if we are in a risk-neutral world, then there are no arbitrage opportunities. That is a very important statement, of course, because it means we are in a market where there's a fair price, where there's a fair price model. And the proof is as follows. Let P tilde be the risk-neutral measure, and let xt, little t between 0 and capital T, be the portfolio process, such that x0 is equal to 0. And now let's assume that the probability of xt, the portfolio process at final time, xt being greater or equal to 0, that probability is equal to 1. Then we will show, that the probability of x at final time being greater or equal to 0 should be equal to 0. So the fact that there's a 0 here is the notion of no arbitrage. When there's greater than 0 here, and let's look back at the definition, when there's a greater than 0, we are in the setting of an arbitrage opportunity. But the fact that we have written here, then we will show that the probability that the portfolio process at final time is greater than 0, that probability is equal to 0, is the notion that we do not admit arbitrage. First of all, we have equivalent measures. P is equivalent to P tilde. And we have that the probability, the P tilde of xt at final time t is greater or equal to 1. When that is equal to 1, then of course with a discount factor at final time being also greater than 0, we would also have that P tilde of dt xt is greater or equal to 0 with capital T here, is equal to 1, right? We can take the discount in. Now, these are equivalent measures, so this is an equivalence. The fact that they have the same null sets, and looking a bit deeper into that equivalent measure aspect means that if the probability P x at final time is greater or equal to 0 is equal to 1, will also give us that the probability under the P tilde measure of x at final time being greater or equal to 0 is equal to 1. That is the fact that P is equivalent to P tilde. And then the other aspect is that if we add the discounting to the story, then we look at the probability under measure P tilde of the discount T xt being greater or equal to 0, that is also equal to 1. Now we know, so if we have this under P tilde, we know that the discounted portfolio process, dt xt, little t between 0 and capital T, we know that this is a martingale under P tilde. And therefore we have that in expectation under the measure P tilde, so the expectation sign with a tilde on top of the discounted portfolio process at final time, that is equal to the expectation under the measure P tilde of the portfolio process at 0 times the discount at 0, which is equal to 1, and this expectation is equal to 0. Now that gives us, this implies when this expectation is equal to 0, this implies that the discounted portfolio process at time capital T is equal to 0, P almost surely. Or in other words, that the probability under P tilde measure of the discounted portfolio process at final time being greater than 0 is then equal to 0, right? Because it is equal to 0, P almost surely, and therefore this should hold under the P tilde measure. And again, because these probabilities measures are equivalent measures, we also have that the probability P of the discounted portfolio process at final time being greater or equal to 0, being greater to 0, is equal to 0 as well. And again, that tells us that the discounted portfolio process at final time capital T is equal to 0, and now P almost surely, right? And because the discounting is greater than 0, then it tells us that xt is equal to 0, P almost surely. And in fact, the probability of xt being greater than 0 is then equal to 0. If we have xt is equal to 0, P almost surely, it confirms that the probability that x at final time would be greater than 0 is in fact equal to 0. And that is what we wanted to prove. I would also like to conclude today with the notion of complete markets. a market model is complete, is said to be complete if every derivative security, so if every option or if every financial contract, derivative security stands for option contract, for example, can be hedged. So if there is a self-financing portfolio, or also called a hedging portfolio, so that at any time little t, between 0 and capital T, xt is equal to vt. The value of the portfolio process is equal to the value of the option. Where xt is indeed the value of the portfolio at time little t, and vt is the value or the price of the financial derivative if sold at time little t. Now, a remark here is that we have seen before that the market price equations, and they look like this: alpha I t minus RT is equal to the sum J is equal to 1 to D, sigma IJT, theta JT. And these are M equations. I is running from 1 to M. When they can be solved for theta, theta 1, theta 2, theta 3, up to theta D. If this solution can be established, then we have a risk-neutral measure, P tilde, and under this risk-neutral measure, the discounted price process, dt xt, for little t between 0 and capital T, that then satisfies, first of all, at any time it is self-financing, so the portfolio process is equal to the option value. Secondly, the discounted portfolio process for all the contract time is a martingale under P tilde. And thirdly, and that is important, we can use the martingale representation theorem, the multidimensional version of the martingale representation theorem, to state that there is an adapted process gamma, a vector valued process gamma, consisting of gamma 1t up to gamma dt in the contract time again, such that the discounted portfolio process dt xt is equal to the discounted option price dt vt, and that is equal to x0 plus the sum, j is 1 to d, the integral from 0 to t, gamma ju dw tilde ju. So the martingale representation theorem tells us there is a gamma. Yeah, there is a gamma j exists, so that this holds. Now that is important. Before, when I run so quickly through the slides, because we did that a couple of video lectures ago, we have seen another expression for this discounted portfolio process. And that was this expression. So we've seen before, but before means a few lectures ago, that the discounted portfolio process could be written as x0 plus a sum I runs from 1 to m over the number of stocks. The sum j runs from 1 to d over the number of Brownian motions. And then we had the integral from 0 to t of delta iu, the number of stocks in our portfolio, delta iu, times the discount at time u, times si at u, times sigma iju dw tilde ju. And so this was our multidimensional version for the discounted portfolio process. And again, it looks very similarly to the one-dimensional case, only we now have these sums in front. And with that gamma from the previous slide, basically we now have a qualitative statement that there is a gamma, and that gamma is then in fact equal to this term. So what we see from these two is that the martingale representation theorem tells us there is a gamma j. For j running from 1 to d, there is a gamma j. And the detailed evaluation of the notion of martingale, the detailed evaluation tells us it looks as follows. It is the sum I runs from 1 to m, delta iu, times the discount factor at time u, times the ith stock price process at time u, times sigma ij at u, and j is running from 1 to d. So the martingale representation theorem tells us there is a gamma, and it looks like this. And with this, of course, we can use this equality to look for the individual delta i's. So this forms the basis, the solution of this system forms the basis for the number of, the delta, the number of stocks of stock 1 until to stock M, the number of stock 1, the number of stock 2, the number of stock M, delta 1T, delta 2T, delta MT, the number of stocks that we should keep in our portfolio in order to build a hedging portfolio so that we have a self-financing portfolio. And you see the time dependency, it is not a constant number of stocks, right? It should change from time step to time step. We should adapt the number of stocks in our portfolio as a writer in order to match the option value. And when we do that, at final time, we have the number of stocks and the number of cash in our portfolio to pay out if the holder decides to exercise. With this, I conclude today's lecture. I thank you for your attention.